Hello, students. Let's begin today's journey into one of the most fascinating chapters in chemistry, the periodic table. Think about this in your kitchen. How easy would it be to cook if all the spices, sugar, and salt were just thrown together in one big box? Impossible, right? That's exactly the challenge chemists faced with elements. As more and more elements were discovered, studying each one separately became chaotic. So, just like a librarian arranges books according to subjects, chemists realized that elements too must be classified for easier understanding. At first, they tried dividing elements as metals and nonmetals. But soon, this approach failed because some elements like arsenic and antimony behaved both like metals and nonmetals. Clearly, a deeper property had to be chosen. That's when scientists turned to atomic weights, a measurable, scientific property that could guide classification. This simple yet powerful idea paved the way for modern chemistry. Let's go back to the year 1817, where a German chemist named Johann Wolfgang Dobereiner tried to bring order to the chaos. He noticed that certain elements could be grouped in threes called triads, where all three had similar chemical properties. This wasn't just coincidence. He proposed what is now known as Dobereiner's Law of Triads. According to this law, if you arrange chemically similar elements in order of their atomic weights, the atomic weight of the middle element is roughly the arithmetic mean of the other two. For example, consider the alkali metals, lithium with atomic weight 7, sodium with 23, and potassium with 39. If we take the average of lithium and potassium, open bracket 7 plus 39 close bracket divided by 2, we get 23, which exactly matches sodium's atomic weight. Amazing, isn't it? For the first time, chemistry showed a numerical relationship between atomic weight and chemical properties. You can see this simple but elegant triad on your screen. Dobereiner's triads gave chemistry its first real hint of order. The strength of his method was that it connected atomic weights with chemical reactivity and properties. If you knew two elements in a triad, you could predict something about the third. But of course, like any early theory, it had limitations. Only a handful of elements could be grouped this way, while many others simply didn't fit. And even within some triads, the elements did not share obvious similarities in chemical behavior. In other words, Dobereiner's system was a good beginning, but it wasn't universal. It was like trying to fit a few pieces of a puzzle while the rest remained scattered. Fast forward to 1866, and we meet John Newlands, an English chemist with a love for both music and chemistry. He arranged elements in increasing order of their atomic weights and noticed something astonishing. Every eighth element repeated properties of the first one. Just like in music, where the eighth note is similar to the first note in the scale, elements too seem to have a musical rhythm. He called this the law of octaves. For instance, lithium and sodium showed similarities, beryllium and magnesium too showed resemblance, just like the notes sa, re, ga, ma, pa, dha, ni, sa in Indian classical music. This was a bold and imaginative leap, as Newlands connected chemistry to the harmony of music. On your screen now, you can see Newlands' arrangement of elements according to octaves. But let's test this law. For the lighter elements up to calcium, the pattern worked really well. Sodium indeed resembled lithium, magnesium resembled beryllium, and so on. However, beyond calcium, the pattern started breaking down. Imagine trying to play music where suddenly every eighth note doesn't match the melody. That's what happened here. Newlands even placed cobalt and nickel, which are very different from fluorine and chlorine, in the same column. To keep the law intact, he sometimes forced two elements into the same position, which made other chemists criticize his work. Clearly, the law of octaves wasn't universal. Yet, It was historically significant because it suggested for the first time that chemical properties repeated periodically, and that idea was a milestone on the road to the modern periodic table. Let's do a quick calculation to see the law of triads in action. According to Dobereiner's law, the atomic weight of the middle element should be the average of the first and the third. Take lithium with atomic weight 7 and potassium with atomic weight 39. Now, let's calculate the mean. At 7 and 39, we get 46. Divide that by 2 and we get 23. And what is the atomic weight of sodium, the middle element? Exactly 23. This perfect match shows how triads provided evidence that atomic weight was more than just a number, it garnered chemical similarity too. Though the method was limited, it gave chemists a hint that the secrets of elements lay hidden in their atomic weights. Let's quickly revise what we've learned today. We began with the need for classification of elements because studying them one by one was impossible. The early attempt of classifying elements as metals and nonmetals failed because of exceptions like arsenic. Dobereiner introduced the concept of triads, where the middle element's atomic weight was the average of the other two, but it worked for only a handful of groups. Newlands then came in with his law of octaves, linking chemistry to music, where every eighth element resembled the first. It was successful for light elements but failed miserably with heavier ones. Still, both of these attempts were stepping stones towards something greater, Mendeleev's periodic table and eventually the modern periodic table. I hope now you can see how chemistry is a story of trial and error, of scientists spotting patterns and building on each other's work. In our next session, we will explore Mendeleev's groundbreaking classification that changed chemistry forever. Until then, keep your curiosity alive because chemistry is not just equations, it's the melody of matter itself.